Thank you, everyone, and thank you especially to the organizers. It's great to be here. It was a great 3 weeks for me, at least, after 2 years of pandemic. So after Ibrahim's talk, which focused on the flavor and the energy of astrophysical neutrinos or high energy neutrinos, in a sense, I'm going to talk about where they might or hopefully are coming from, and what do we know about the sources that are producing them and what we can do in terms of neutrino physics system with them. So the idea of neutrino astronomy or astrophysics emerged very soon after the discovery of neutrinos, and it's because neutrinos can give you a view of the universe where the universe is basically opaque to the gamma rays, photons that we are used to look into the universe with. So in the vicinity of the monstrous environments in the universe, like active galactic nuclei, black holes that have just, for instance, accelerated cosmic rays would interact with the environment, gas or radiation that you have, produce charged and neutral pions. They would decay into neutrinos and gamma rays. And unlike the gamma rays that can be absorbed, and unlike the cosmic rays that can be bent or stopped by the gas, the neutrinos can point back to their sources. So they basically provide a strong tool, an idealistic tool to do astronomy and actually solve the cosmic ray puzzle that has been unanswered for more than a century. And they can give us a window to the very extreme universe between 10 TeV and 10 eV, 10 to the 19 electron volts. The challenge, of course, is that the statistics is low, the background is large, and it's hard to do so. So you heard about the observation of high energy neutrino flux in 3 different channels, basically, that Ibrahim showed you. And this is the arrival direction of the most energetic events that we have in IceCube. So the magenta lines show the cascades, which have large angular uncertainties. The smaller circles with a dot in them are the tracks, which are good in angular resolution. And you can see that most of them are around the horizon. That's where we have the best sensitivity. And there are scarce when you go towards, looking towards the Earth, where you have the absorption. Since there are no significant clustering of these events, the high energy ones, this is predominantly understood to be from extragalactic sources. You don't see clustering around the galaxy. So this is more or less isotropic in arrival direction. And when we do the search for the origin of these neutrinos, we look into all the neutrinos we have, including the one that come from the atmosphere. And that's how it would look like. We have more than 100,000 neutrinos in 1 year in both hemispheres. And without showing the uncertainties, this is how it looks like in galactic coordinates. So this is the North Pole, this is the South Pole. This little structured data that you see here is the horizon for IceCube, which the effective area is the largest. So what are the possible sources? In order to produce sources with neutrinos that have energies greater than TeV, you need a cosmic ray accelerator that can provide energies of beyond TeV. A neutrino has basically about 5% of the original cosmic ray energy. And the other thing that you need is a beam dump. An area, an environment that has enough density that facilitates the interaction of cosmic rays with either protons, the dust, gas, or with the radiation that comes from these environments. This is similar to the setup that we have in an accelerator on Earth. So you accelerate a proton, you shoot it into a beam dump, and then you have mesons produced decaying into neutrinos. So the primary candidates are the ones that can actually accelerate cosmic rays. Supernova remnants has been long understood to be able to do this. The shock accelerates into the molecular clouds. The interaction is facilitated, and you can have neutrinos. Gamma ray bursts are one of the gigantic explosions that we can have in the universe. There is a jet, and the particle acceleration there with enough density can provide neutrinos. And active galactic nuclei, where you have a supermassive black hole with a dense core that also has a jet of particles coming out, is one of the other candidates to produce high energy neutrinos. So the connection between the neutrino and gamma rays, usually referred to as the multi-messenger astronomy, is basically made when the charge and neutral mesons are produced. So the pi zeros will give you the gamma rays, pi plus and pi minuses would give you the neutrinos, and the neutrino production is governed by the kinematics. So you have to meet the threshold for pion production, or at higher energies for the production of delta meson. The gamma rays are produced, their arrival at Earth depends on the pair production. So if they are more energetic than the threshold for the pair production, they will cascade down and you would not see them at the energies that they are produced at the Earth. So at the source, you can relate the rate of neutrino production and the rate of gamma ray production. But if the source is opaque, if it's suppressing gamma rays, or if the source is far enough, the absorption in the extragalactic background light will suppress this flux and you wouldn't see that at Earth. So how do we do these searches for the origin of cosmic neutrinos? I'm introducing this here in order to avoid using the jargons here. So the first way to look for the origin of cosmic neutrinos is to look for the clustering of the events. So it's basically autocorrelation. We look into the data, we scan over right ascension and declination, basically, to see if there is any excess over the background. The other way is to have a source or a source list, and we look around those sources in order to find if we can find an excess. The benefit here is that it reduces the number of the number of trials that you do, because if you want to scan the whole sky, you will suffer a lot of trials, and the chances are you run into some excess by accident. Another powerful way is to do a stacking search when you look for a collective neutrino emission from a bunch of sources. So which is good in order to understand whether a class of source is emitting neutrinos or not. Adding to that is the real-time analysis and alerts that IceCube produces in order for other telescopes to look for if there's anything in the direction of any high energy events that we observe. So first, I'm going to talk about what are the recent developments in identification of high energy neutrinos. And the most recent results that we have is the 10-year analysis of IceCube all-sky time integrated search. So this is the whole sky in equatorial coordinates. This is the horizon, the galactic center is here. And these 2 points are the northern and southern sky hotspot. Basically, these blue dots are showing the p-values, and this is where you find the most significant spot in the sky. The p-value is better than 10 to the power minus 6 for this point. And when you look at the list of sources, basically 110 sources that we look into, these triangles show where the best fit and upper limits are. And as you can see, there are sources that stand above the sensitivity line for different spectrums that we assume here. And interestingly, 4 sources here stand above the 4 sigma line pre-trial in our analysis. And one of the most important aspects of these 4 sources is that they are all active galactic nucleus. So I'm going to focus on these 2 sources that are the prominent sources here and discuss why this is quite interesting and why the fact that we selected 110 sources and found 4 sources to be as significant is basically telling us that we are seeing signs of anisotropy in the neutrino sky. So the first interesting feature is the hottest spot and the hottest source are coincident. So I told you that this point in the northern sky is the hottest spot when you do the clustering search. So we do an untriggered search over the whole sky and find this place. And we also had a pre-selected 110 source list. And this point in the sky, that is the hottest point, is coincident with the hottest source in that list, which is NGC 1068. And the trial corrected significance for this source becomes a 2.9 sigma, basically shadowing the 3 sigma threshold that we set for the evidence. So let's talk more about the NGC 1068 and the signal that IceCube sees. So NGC 1068, also known as Messier 77, is a Seyfert-2 galaxy with a heavily obscured core. It is actually one of the best studied AGN and has played a major role in the AGN unification scheme that we know today. And its core is actually about 10 to the 25 centimeter squared inverse, which is quite dense. And it's very bright in X-ray. In fact, X-rays get absorbed in this source. It has a very high infrared luminosity, which can indicate the star formation. And subsequently, it is historically considered as a promising source. Then this is what IceCube sees towards this source in terms of flux and energy. So the 10-year time-integrated search finds 51 neutrinos in the direction of the source. It fits a quite soft flux for this source. It's about e to the power minus 3.2. And you can compare this flux to the one that is seen by MAGIC and Fermi. And as you can see, it is about 2 orders of magnitude larger than the gamma ray flux that these telescopes observe, which means that models that have been originally built based on the assumption of the gamma ray flux that is observed from these sources cannot describe this level of neutrino flux that we see. And the necessary condition here is that you need obscuration at the source in order to suppress the gamma rays that are produced simultaneously with the pi plus and pi minus in the source. So let's look at what can explain this. In the terms of obscure sources, the medium energy excess in the neutrino flux plays a major role and is connected to what we're talking about. So this is what was the discussion that Ibrahim said and Joachim had a question about. These are the 3 channels that IceCube sees neutrinos, neutrino fluxes, and you can see they have different slopes when it comes to the power law. The upper part of this, at around 30 to 60 TeV, is about an order of magnitude larger than the highest energy part, about 1 PeV or 100 PeV. This is usually referred to as medium energy excess, and in order to fit into the multi-messenger connection, which means that neutrinos and pions and gamma rays that are produced will propagate back, they create an extra background, galactic background in the gamma rays. If you have neutrinos here, and if the sources are transparent, you are going to overshoot what Fermi sees. So whatever produces this region has to suppress gamma rays into MeV or KeV in order to avoid violating Fermi. And NGC 1068 actually fits into this scenario. And the model that, one of the models that can actually describe it is referred to as disk corona model. I'm sure nobody is amazed to hear corona in this situation, but the accretion dynamic and the high magnetic field and the thermalization above the core of Seyfert galaxies produces a hot corona above the core, which is quite dense, and that corona interacting with the disk, the accretion disk, provides the means for the production of what we refer to as the medium energy excess in the neutrino flux. And in terms of NGC 1068, assuming a high cosmic ray pressure in this model can actually accommodate the flux that IceCube sees at these energies. If you look at the 10 brightest Seyfert galaxies that are observed in X-ray surveys, this is the flux that you would expect. And if you adapt for the parameters that can describe NGC 1068. And if you look at these red lines for these other 9 sources, you can see how high the fluxes can be. But the interesting thing is, if you look at the prospects, NGC 1068 actually appears as the most significant source in the sky, thanks to its vicinity to us and its location, which is close to the horizon for IceCube. The good thing is that in the near future, NGC 1068, KM3net, can look into the other sources that are in the southern hemisphere and test whether this model works and if we can see more sources like NGC 1068. Further in the future and with moderate values of the parameter space, you can see that KM3net and IceCube Gen 2 can actually test this scenario even with very poor angular resolutions, which is unlikely. We are hoping for better than 0.3 degrees with these detectors. So I talked about NGC 1068, and NGC 1068 was the most significant source in IceCube list. Now I'm moving towards the Blazar TXS 05056. And this is the source that was identified in 2017, published later in 2018. And this was the first multi-messenger source that was observed in high-energy neutrino astrophysics. So in September 2017, we had an upgoing track which issued an alert into the other telescopes. And it was coming about near the horizon with the 300 TeV passing through the detector. And when followed up by other instruments, the major thing was that Fermi and MAGIC saw enhancement in gamma ray activity. So you had a neutrino, you saw very high energy gamma rays, and it led to a multi-messenger campaign. You can see all the non-gray points in this plot are the follow-ups that has been done. And as you can see, the neutrino is very close to this source. Then IceCube did an archival search study in the direction of this source. And it appeared that if you do a time-dependent search, in the period of 2014 to 2015, in a period of 6 months, there is another flare of neutrinos in the direction with about 13 neutrinos for 110 days, and 13 plus 5 neutrinos are observed here. The challenge here was that there was no gamma ray flux during this period. So the source is quite silent in gamma rays when it comes to neutrinos. So the gamma ray neutrino connection after this realization was seemed to be a little more challenging and complicated than it was observed. The first thing is that you saw that we had 3 results on the NGC 1068. One was the coincidence with the gamma ray enhancement that was in 2017. Then there was the archival flare that was in 2014-15 season. And then it was the time-integrated 10-year analysis, which also identified NGC TXS. But the important thing is that the flux from the TXS is dominated by the burst from 2014. And there's a slight hint for a little hardening of the spectrum, though it's not significant. And it becomes challenging describing the spectrum of the source with one-zone models, which basically try to explain this, the broadband spectrum, multi-wavelength spectrum of blazars with acceleration in one particular location in the AGN. So you can describe the absence of the gamma rays with the absorption and in the source, and then propagation of gamma rays in the EBL when intergalactic magnetic field is large. However, there is going to be X-rays that are supposed to be accompanying these fluxes, and those are not seen, which makes it quite challenging still to model the source. And we probably have to move toward 2-zone models, but the number of parameters here are quite large. Another interesting feature was that enhanced radio emission was observed by Ovrov and VLBI in the period of 2014 flare. So you see this rise, and before the 2017 flare. So the emerging feature after that became that you could see gamma ray silent blazars that are coincident with one neutrinos. So this is the one that was coincident with the PEV neutrino in the cascade data. This is the TXS. This is another alert, 1907-30, that was coincident with an alert. And again, it was in a gamma ray quiet mode. And this is becoming a feature of these sources. And there are more coincidences here. This one I mentioned, you see again, gamma rays are low, but radio is rising. Another blazar was found coincident. And there is also coincidence with radio enhancement that is seen by VLBI or OVRO, which is quite interesting, but it is not yet conclusive because the radio varies a lot. Another interesting emergence is the coincidence with the tidal disruption events. These are these fascinating astrophysical scenarios that a black hole, an AGN, is ripping off another star. And two of these rare events are actually seen coincident with a high energy neutrino alert. And there are studies that suggest common origin of this, but we need more data to basically have a more coherent picture. Okay, another prospective source of high energy neutrinos is galactic neutrinos, and in principle, we are considering galactic sources as one of the guaranteed components of the astrophysical neutrino flux. So we know that part of the cosmic ray spectrum is produced in the galaxy. There is the vague region, and after some energy, we expect it to be extragalactic. So the galactic cosmic neutrino search is basically focusing on tevatros, which are sources that can produce the cosmic rays around the knee of the cosmic ray spectrum. And again, the supernova remnants are the ones that can meet this condition. So the major sources in the galaxy are supernova remnants that I mentioned, X-ray binaries or microquasars, pulsar wind nebulae, and diffuse galactic emission. This is what happens when the galactic cosmic rays diffuse through the galaxy, interact with the dust, and produce an extended neutrino emission. So, and we have done these searches. We have looked for supernova remnants in a joint analysis with HAWK. We have looked at the pulsar wind nebulae, which are the major TeV emitters in the galaxy, binary sources, and diffuse galactic emission. And what all these searches have in common is that we are getting sensitive to test this. So this is what we actually knew a priori, that more than 10 years of IceCube is actually needed to pin down this. And we are closing in on the parameter space. So you can see that the sensitivity is reaching here. The sensitivity for the diffuse flux is touching the predictions. And this is what we're expecting to see in the near years of IceCube. So another interesting prospective source that I want to talk about here is the core collapse supernovae. And we have heard enough about the importance of the core collapse phenomena in neutrino physics and what they offer. And there is growing evidence that the expansion after the supernovae happens is much rapid, and there's a mass loss that can provide the circumstellar material that can facilitate production of high energy neutrinos. What it means is that about less than a day or up to 10 days, depending on the type of supernova, you would expect a high statistics on the TeV emission from the supernovae. So the type 2N has the highest luminosity, the other ones has less, and type 2P, which is the most frequent one, will have more. So, and this is coming from the H-alpha observation of the extragalactic supernovae that are observed in optical surveys. So, if we look at the supernova type 2P, which is the most common type of core collapse supernovae, we see that previous estimates actually included a fluence of around 100 GeV per centimeter squared. And he have been visiting this, and this is based on the observations that have revealed that the mass ejection is much larger than actually expected. And because of that, we are revising this flux to be about 2 orders of magnitude larger than expected, which given the most frequent, the higher frequency of supernova type 2P provides a higher chance of observation in IceCube. And I should mention that this is for a 10 kiloparsec supernova at 10 kiloparsec, and the IceCube sensitivity to this kind of time-dependent emission is around here. So you see, IceCube would be actually overwhelmed if this would happen. We would have more than 1,000 neutrinos or near 1 million for type 2N. So this is what we would expect if the core collapse happened in the vicinity of the galaxy. So forget about the center of the galaxy, and let's go a little further to the neighborhood. And you can see for type 2N, the IceCube can see up to about 4 megaparsecs, 1 or 2 or more 3 events based on these thin lines. And we have IceCube Gen 2 or the network of the northern hemisphere telescopes, which increase the size, we can go beyond 7 PeV, 7 megaparsecs. However, the rate is quite low. So for the supernova type 2N, the chances that we have is less. But for supernova type 2P, in the optimistic scenario that I showed you, this could go about 2 or 3 megaparsec, and Gen 2 can push it about 5 megaparsec. So which gives us a very good chance of observing a supernova. If we look at the nearby galaxies, the local galaxies, including LMC and SMC, current telescopes can provide enough significance if a supernova goes up to type 2P. And if we combine the data from different detectors, this can be pushed back, and we can see that up to about 2 megaparsec, we can have significance detection of high energy neutrinos from core collapse supernovae. So another thing that I'm going to mention here before switching topic is the tau neutrinos and the power that they give us to look at the sources. The sources that I was mentioning were mostly sources that produce high energy neutrinos in the range of TeV to PeV. And there are a lot of sources proposed that can produce neutrinos at much higher energies, and which we usually refer to as ultra high energy sources. And this is the blue line here is the conventional, the sensitivity to point sources in IceCube. And as Brian told you, we can have regeneration of tau neutrinos. And if you include that, you become sensitive to another set of classes, which can also bring you enough sensitivity to do a lot of neutrino physical stuff at very high energies. Okay, let me switch gears here and talk about how we can probe for new physics when we have direction and we can use it. So the circumference of this Venn diagram here shows the observables of high energy neutrinos. And the center you can see different beyond the standard model scenarios. And they would relate to the energy or flavor and also direction and time. And I'm going to go in this diameter, talking about some of these events that can actually be understood from the observation of the anisotropy or the sources. So one thing that we can do is to go after the dark matter annihilation signatures. And this is quite fascinating that we have actually an uninterrupted measurement for neutrinos below, let's say, GeV to above, let's say, 1 eV, or the sensitivity. You can see that there are places that we are touching the thermal lake abundance. And here is where the high energy neutrino telescopes work. And this mainly uses the energy to limit the dark matter annihilation to neutrinos. However, the strongest limits come from the fact that some of these experiments can provide you the direction. And that's where the galactic center is, right? If you can find the neutrinos in the galactic towards the galactic center, that's where the dark matter has its most density. We are doing the same for dark matter decay. And as you can see in the range that we have these high energy neutrino telescopes, we have much severe constraint on the dark matter lifetime. Another thing that is the benefit or the advantage of identifying sources comes from when we look at the galactic clusters or halos of galaxies. In Kev's talk yesterday, you heard about how Virgo can be important. This is the prospective sensitivity that we would have towards Virgo. I should have mentioned Virgo on the title here. So the thick lines here are when we include an astrophysical neutrino flux background if we want to identify neutrino flux towards Virgo. But if we can remove that background, if we understand that background, we can go to these thin lines, which is the background free regime. And you can see that this can be moved up and we can constrain dark matter, very heavy dark matter lifetime much better than we can do today. And in the era that we have Gen 2 and other detectors, this can be done much better than what we do with the diffuse fluxes. Okay, another thing is the dark matter neutrino interaction and dark matter and neutrino secret interactions. if we have an isotropic flux of high energy neutrinos, the ones that pass through the center of galaxy would experience more dark matter neutrino interaction, which would create anisotropy and also energy loss in the direction of the galactic center. So this is the IceCube events overlaid on top of the dark matter density. And if we include the effects without interaction, this is what you would expect. So this is plain. And this is about 500 years of IceCube. So this is just for simulation. But if there is a strong interaction, you would expect a deficit towards the galactic center. And this deficit and the energy information could be translated into what we see in the data. So you can see dips in the energy, or you can see that the number of events away from the galactic center would increase. And when you put into a likelihood analysis, you can see that with about 4 years of IceCube, you are able to constrain parts of this parameter space depending on the type of the dark matter and the mediator better than what we see in the cosmology. Okay, the final thing I'm going to mention is how we can use the time to do this. And this is the idea that Morales and Shoemaker actually did after we had the first sign for TXS. So if you have a transient, you have a very short time that neutrinos would arrive. And if there is interaction, the time of the travel time that neutrinos have would be elongated compared to the ones that come from the gamma rays. So this is a temporal profile that you would expect. So depending on the distance of the source, most of the neutrinos would arrive at a specific time, which is longer than the duration that you would usually require. And that can be translated into the constraint on the interaction, the strength, the coupling, and the mass. Okay, I end up here with the summary. We have first signed up anisotropy after about 10 years of IceCube operation. Early indications are pointing towards active galactic nuclei as the prominent origin of cosmic neutrinos. We have other prospective sources like galactic sources and core collapse supernovae. And there is a complementarity and new opportunities when it comes to the testing beyond the standard model with neutrinos at the highest energies. And identification of the sources would provide a very powerful tool to do so. Thank you.
Okay, thanks very much. Do we have any questions?
Thanks. There's a lot there. I'm going to ask about something that wasn't there, I think.
Okay.
So one of my colleagues at UCI, Toshi Tajima, and his colleague, or his collaborator, Toshi Ebusuzaki, are very enthusiastic about Alpha wave acceleration mechanisms in AGN and also other jets. And they have ideas as to flavor content, well, not flavor content as much as gamma ray and neutrino flux correlations and timings. And I've heard these acceleration mechanisms mentioned by IceCube and other high energy neutrino experimental overviews, but I don't see much work outside of kind of this narrow group working on it. What are your thoughts on that mechanism?
Okay, so there are, if I put it in correct ways, correct name, terminology, there are old-fashioned ways of acceleration that people have considered, like Fermi second-order acceleration and things like that, that are quite established. And there are other forms of acceleration, like the stochastic acceleration or magnetic reconnection, that are becoming more fashionable and actually look more reasonable, to my understanding, for explaining a lot of the physical phenomena that we are seeing. So when it comes to the very high energy part of the spectrum, the old-fashioned ones still look reasonable and working. But when it comes to NGC 1068, if you look at this, this plot here, so I have two scenarios here, a stochastic acceleration and magnetic reconnection, which I didn't talk that much about, right? And these are relatively new in terms of what we do in neutrino physics, or to look for the sources might not be very new to people who do cosmic ray acceleration mechanism like your colleagues. But these are not as established as we know. And these are becoming the more prominent ones to describe this low energy part of the spectrum, apparently. And also there is a synergy with the, for instance, tidal disruption events that can be. So I'm not personally familiar with what you were referring to, but if I'm guessing correctly, these scenarios are going to be very important in terms of what IceCube sees, especially if you are going to see more tidal disruption events, if actually this corona model is correct, because, for instance, the threefold model is not supported by the simulation. In that regard, I would expect it to become very important in terms of what we would predict for observing in IceCube. Whether or not we can distinguish the different models would depend on the significance of observation of the source. Because if the sources are not as efficient, or the particle acceleration mechanism is not as efficient, we should not be seeing a strong source like this.
Thank you.
In the context of that blazar, the Texas or whatever source, you mentioned that you have data from a couple of blazars that have coincident neutrino events, but no coincident gamma rays, right?
Yes.
Could that indicate something like there being an outflow from those blazars that just hit something to make neutrinos, but that something is optically thick to photons?
That is the primary indication. Yes. So
but it doesn't. I wasn't quite sure if you were saying that this indicates that there's just something special going on, or if this makes it less likely that blazars are one of the main sources of high energy cosmic rays.
Neither. With one event, it is not much that we can say, more than that there is a coincidence.
But so those other events that you showed that had a high energy neutrino from the direction of a blazar, but no coincident gamma rays, was that the same blazar, or?
No,
these are not different ones, right?
These are different blazars. These two are FSRQs. This is a BLAC. These are different things.
So in principle, one could hypothesize that these are all high energy neutrino sources, just they do it in a way that doesn't make gamma rays.
Yes, but if you do a hypothesis test, because of the low statistics, it doesn't turn out as significant as you
okay.
want. Right.
Okay, thank you.
So your statement is correct that if these are sources of these high energy neutrinos, they are in the scenario that you express, the prescription that you provided is responsible for the production of them, right? But remember that when we talk about one neutrino, this, for instance, for one particular neutrino has a 50% chance of being atmospheric.
Right.
Right. So the likelihood analysis becomes a little more complicated when deriving the significance for these observations.
Okay, thank you.
Okay, do we have any more?
Alex.
Oh, Alex, thank you.
So correct me if I remember the history of this accurately. So before the observation, there was a sort of a generic physics argument about AGNs. The generic argument said that there is a jet, there are internal shocks, there is Lorentz boost of a factor of 100 and something like that, and the prediction was 10 to the 18 EV was what people started thinking about. And the first set of searches at IceCube was actually looking there, right?
Yes.
And so now we see these events, and they are, maybe starting to correlate with blazars, but the energies are 10 to the 14, 10 to the 15. So what has changed in the physics understanding to explain this?
So I think it depends on who you ask. The answer to that question. I try to answer it in terms of what we have seen so far, right? Not necessarily in terms of. So if you are quite right about.
I mean, to put it another way, right? Now the reference models that you build to explain it don't look like the models
Yes.
of the past. So I'm asking in which way, like what
So
is the
one of the things that has changed is, for instance, if you look at scenarios that are described here for TDE, right? The location that the interaction happens changes, right? So you, like the old Blazar models, if you're looking at BLX, for instance, try to describe the high energy emission with the blob that is accelerated through the jet, right? That's where you have Lorentz factors larger than 100. And that's where you have the target photon that is at the synchrotron level. So it's about 100 keVs or maybe larger. So when you have that you can have different energy, right? If you go to FSR, lattice spectrum radio quasars, your target photon is UV. So you have to have a very higher energy. So instead of 10 to the 16 or 17, you have to go to 10 to the 18 and 19 in order to produce neutrinos in a P gamma interaction, right? So the assumptions here are changing. For instance, in the work that was done prior to this by Bierman and company, if I can find it, there's this one, yeah. So there's an interesting morphology of the jet that has been studied. You can see that the jet, it's not very easy to see the cyan line here. But the jet is evolving here, and their assessment of the Lorentz factor is about 10, right? So this is what has changed. So if you assume that the interaction happens near the core, not at the foot of the jet, right? You are basically pushing your energetics toward lower energies, and that's what happens in the IceCube. In fact, if you forget about the Blazar classification, look at radio galaxies. We actually showed that you can have this flux that IceCube sees around 100 TeV and above if you just have enough density near the core, which is low Lorentz factor, enough accretion, and in fact, without any gamma photons, you just need protons. But it cannot describe the whole story because you have the lower energy part still. Still, people are quite faithful to what you described. For instance, if you look at the models that try to describe one of the alerts that I was showing. Yeah, for instance, since it is one event, it's a lot of freedom and it's a lot of also restrictions, right? So for instance, this is an extreme blazar. We can have that scenario, and this so for Votini et al. Have a model that can describe this, but the actual neutrino energy is above 10 PeV, so it's much higher. So going back to your question, I think the main thing that has changed is where the interaction is happening. It's not necessarily in the jet.
Do you need the jet anymore? Maybe you don't.
Maybe no. Maybe. Now, for instance, for the NGC1060 scenario, you don't need the jet, and that's all. If the Corona model actually works for TDEs, you also don't need the jet.
I was going to ask. So, do we know about if there is a jet in this TDE, the one that is?
So this is a bit controversial because we have seen the radio from it. But my understanding is that it's not conclusive.
Okay, we're basically at 3:30. If there are no other questions, we should thank Ali again.